Thank you all for stopping by to another Talks at Google presentation. This afternoon's talk is with Marcelo Gleiser, who is a professor of physics and astronomy at Dartmouth College, and he's made numerous contributions to research and both science and also science in the popular eye. His contributions to physics and cosmology include being the co-discoverer of oscillions and the publishing of numerous articles. And his research and his books have actually wound up in the publishing of 4 books, including A Tear at the Edge of Creation and The Dancing Universe. Today he speaks to us on the Island of Knowledge, which blends science and philosophy to trace our search for the answers to life's fundamental questions. And we'll have some time for Q&A at the end, so please join me in welcoming Professor Gleiser to campus. Thank you.
All right. Thank you all for coming. I have been told that there are about 4,000 other people from Google watching remotely, so it's really awesome. Thank you very much, guys, for being there for me. You know, it's really great. And the other thing which I wanted to make a remark, which you guys may or may not know, that there's this real hot debate going on in academia right now about should students take laptops to class or not. It's a big one, you know, and it's a complicated question, actually, to deal with. So what I want to talk about today, and my plan is to talk for maybe 30 minutes or so we have time for questions, which is, to me at least, the more fun part. I will talk about ideas from my latest book, hopefully not the last book, on really big questions. Okay, so this book is dealing with what is reality and how can you tell. And because reality is so much related to the nature of truth, really the book relates how we can figure out truth, and does science actually lead you towards that kind of big T, formulation of what we know in the world. And the answer is kind of humbling. So what this is an exercise on how science actually works. You know, it's what philosophers like to call epistemology. You know, how do we acquire knowledge of reality? And so the first fundamental point is the following, is that how do we know that you're here? How do you know this is happening right now? Well, you know, you have this amazing sensory apparatus, right? You have your eyes and you have your ears. So your organs are picking up information from the environment, right? And they are bringing this information into your brain. And your brain is this amazing thing that can integrate all this sensory information and construct this cognitive image and impression of what reality is, right? So what we call reality, at least from a more immediate way as humans, is this sum total of this sensory integration that is happening in your brain, right? And of course, the point is that is really not all of reality at all. That's just a tiny little fraction of what reality is about. And what else is going on? Well, you know that right now there are tons of electromagnetic waves going through this room, you know, all the FM and AM radio stations from the areas around here. You have ultraviolet radiation from these lights. You have infrared radiation that you guys are beaming out because you're all warm bodies. And when you're a warm body at about 98 degrees Fahrenheit, you're beaming infrared radiation. But all these things you cannot see. But the fact that you can't see it doesn't make it less real, right? So in a very concrete sense, science is an effort to amplify the way we see reality, right? There's this little line from The Little Prince where the fox is talking to the little prince and says that what's invisible is essential to the eye. And essentially, science is trying to uncover, at least modern science is trying to uncover this invisible, right? Kind of opening our eyes to what's going out there. So I wanted to kind of set the mood with a quote from the master himself, from Albert Einstein. And I see there's a Google equals MC squared over there, which is really cool. I had to take a picture of that to show my students. But what he says is the following. What I see in nature is a magnificent structure that we can comprehend only very imperfectly. And that must fill a thinking person with a feeling of humility, right? And what he's trying to say that is almost against what he believed, right? So Einstein was a realist. So he thought that there is order in nature and that there is some sort of pattern that we can uncover with our minds. And it's just a matter of working hard at it, and you can figure things out. That nature, as you probably heard before, he is famous for saying that God doesn't play dice. He wasn't talking about any real God. It was meant nature cannot be random, cannot be unpredictable. There has to be a fundamental order underneath everything. And yet, he also recognized that as humans, we can only go so far in understanding the world, right? And so, in that sense, you can understand things imperfectly, and you should have really a feeling of humility, meaning, you should be humble to understand that you really don't know. There's another quote from Einstein, which I think is relevant in this context, which is this one. The fairest thing we can experience is the mysterious. It is the fundamental emotion which stands at the cradle of true art and science. He who does not know it and can no longer wonder is as good as dead. Right? So basically what he's saying is that wake up, people. There's all this awesome unknown stuff out there, what he calls the mystery, right? What's out there in nature that we do not know. And if you're not excited by trying to figure that out, then you're just not alive. That's just not happening. And furthermore, it is this kind of seductive power that we have to this mystery, to this what we want to figure out, that is the creative engine behind so much art and so much science, right? So he's bringing this sort of human urge to understand into this big umbrella, right? Putting all our creative output, be it artistic or scientific, under this big umbrella, which is this engagement with the unknown, with the mysterious, right? Which is a very interesting position which I share. Right? And then we have this picture here of the fish in the bowl, right? So here's the little fish, and at least when I look at that, well, to me it's a beautiful picture, but it's also kind of sad, right? Because you look at the fish and say, poor little guy, his universe is so confined, right? He is in that little bowl, that's all he sees. I mean, he can kind of glimpse through the glass, there is some stuff out there, but he can never get to it. Much better to be the photographer, right? To be the guy on the outside that can actually take that picture and see the sunset and understand that, hey, my reality is much richer than that of the fish. And the point I'm going to make is it's not really, that our reality is kind of exactly like that of the fish, And so when we conceive, the world and understand what is the world like, you have to be very careful to measure, where you want to take this statement, this is what reality is about, or there is such a thing as a fundamental reality that we try to uncover. And I speak this being a theoretical physicist that works in cosmology and high-energy physics, which is really, the Big Bang and black holes and Higgs particle. That's the kind of stuff I do. I'll be happy to answer questions about that later on. But it's important to understand that when we try to push the boundaries of knowledge, you're always going to hit a certain wall, which is the wall of what we can do to understand what's going on. And furthermore, and here I quote Heisenberg, who is one of the architects of quantum physics, right? He says something very important. He says that what we observe is not nature itself, okay? But it's nature exposed to our method of questioning. And that's really interesting, because what he's telling here is that there is only a human way of understanding things. There is no universal way of understanding things. And that's kind of like rub against our notion that there is such a thing as some universal truth out there, right? That we should be able to get to that, and that is beyond the human frame, right? So that if an alien intelligence can do physics, right, or chemistry, they are going to come up with laws of nature which are just like ours, our laws of nature, right? And what he's saying here is something like, perhaps the content of those laws is similar, but the way they're going to be expressed is completely different. There is a very human way of probing reality, right? And we are animals that evolved in a very specific set of circumstances, right? We have a star about 150 million miles from us, and it has a surface temperature of about 6,000 degrees Celsius, which makes it glow whitish yellow. And so any form of life that evolved in this planet had to maximize the way it could capture this radiation. And hence, we and most of the animals around us can see in this very tiny window of the electromagnetic spectrum, which is what we call the visible, right? From the red to the violet, right? And that makes sense because, if you could see in radio waves or in microwaves, when a tiger comes to you, you're going to be eaten, right? So it doesn't really work very well from a survival perspective. So it's no wonder that our eyes can capture the most power output that the sun can put out. And so when we try to put these things in context, we want to understand what is science trying to do. And there is this philosopher from the 17th century, which is really an awesome guy, called Bernard Le Bovier de Fontenelle. So the same year that Newton published his Principia, right, which is the book that changed the world in a sense, right? It was the book where the laws of motion and the law of gravity was written, 1686. This French philosopher wrote a book on the possibility of life in other planets, right? And it's a really interesting book because it's constructed as a dialogue, sort of inspired by Plato. But in that book, he has two characters. He has the philosopher, which is himself, and a co-protagonist, which is a woman, which is a very, very rare thing in the 17th century, who is much smarter than he is, in the sense that has the sort of the wit, And there's this dialogue between them in which she's always questioning his assumptions from a natural philosophical, which is the old name for science, perspective. And this guy says the following. This is how he summarizes the problem with trying to figure things out, from a scientific perspective. Okay, so he says, all philosophy is based on two things only: curiosity and poor eyesight, right? And I think that's just brilliant, because that is exactly right. I mean, we are super curious. We want to understand things the best possible way, more and more, right? More information. You guys know this better than I do, how hungry people are all the time for more and more information. And yet, we are myopic, right? I mean, there is only so much we can see, right? And there is a tension here about wanting to know a lot and not being able to know everything. And from this creative tension comes, the output from science, right? So this poor eyesight also has to do with our perspective of what reality is like. So now I switch gears and I go back to 400 years or so before Christ, to Plato's cave. Okay, so Plato, in his Republic, in the book 7 of the Republic, he wrote something called the Allegory of the Cave, which is absolutely a brilliant kind of way of thinking about what is the nature of reality and how can we know. Okay, and the notion is about more or less the following. Let's imagine that we are inside a cave, okay? And you guys are the slaves, because that's how Plato framed the stuff. And the slaves were born chained in such a way that all they could do is look forward. Okay, so all you could do is look forward to what's being projected on the cave wall in front of you, right? So for these slaves, reality was what they could see in there, on this cave wall. That was reality. Now, they didn't know that behind them, there was this big, big fire, roaring fire, and a bunch of philosophers, they're holding stuff up, right? And the projection, the shadows from these objects were being projected on the wall, right? And what the slaves saw was just the projection. So they would say like, oh yeah, this is like, one shape, when they have no idea that the true shape is like a rectangle, so to speak. And so here's a variation on that, is when Neo visits Plato's cave, right? Neo from the Matrix, right? And as you probably know, if you don't, you probably couldn't get a job here, right? So in the Matrix, people thought they would be seeing reality, but they weren't seeing reality, right? So here goes Plato, Neo to Plato's cave. There's Keanu Reeves with his machine gun, and it says, the guy next to him says, it is prophesied that one day a chosen one among us will break free of this world and reveal to us the true nature of reality, right? And he says, no way. And you see there the slaves there, right? And what do they see? They see a unicorn pooping, right? And they said, wow, unicorns exist, and they defecate just like we do. And what's really going on is there is that naughty philosopher behind there, right, making little hand signs, right, with his fingers and projecting these things onto the wall, totally fooling the slaves into believing something that is not real, right? So the question is, okay, who are we here? How much can we see of the world and be comfortable with the notion of reality, right? So now we go down to science, right? And I broke this into three parts, okay? So three kinds of realities: the cosmic reality, the universe; material reality, what is stuff made of; and cognitive reality, how do we figure things out with our minds, okay? So to set the tone, let me introduce to you the wonderful things called scientific instruments that you all know about, of course, which I call reality amplifiers, right? And why do I call them reality amplifiers? Well, because they reveal invisible worlds, stuff that we cannot see with our eyes and hear, etc. And they tell you things about the world that you didn't know before. So to give a very specific example, the microscope, right? So the microscope was invented in the late 1600s, right? Now, the conception of what life is before the microscope and after the microscope is profoundly different, right? Because before the microscope, living things were things you could see, right? And after the microscope, you'd look into a drop of water and you see all these invisible creatures that were alive. So all sorts of new questions like, how small can life be? Is there a limit to how small it can be? And are these things related to us? And are these things the things that make us sick? So all this complete new way of thinking about life emerged from that single instrument. The same, obviously, with the telescope and with a bunch of different detectors. I have here in the bottom two of my favorites, right? So anybody knows what this is? The Hubble Space Telescope, right, which is one of the most amazing machines ever invented. Picture this, right? This is a robot telescope, right? So it's a robotic telescope that is orbiting very far away from Earth, just being controlled by remote control here on Earth by astronomers and technicians, and taking pictures that have never been taken before and that completely change the way we understand the universe now. And on the right-hand side is the ATLAS detector from the Large Hadron Collider at CERN, which is the machine that discovered the Higgs, right? And you don't know if you can see this, but there's a little person here, right? It is huge. It's about 4-story high. It has more steel than the whole Eiffel Tower in there, okay? And that's this giant thing we use to study the smallest things that exist, the particles of nature. Okay, so cosmic. Let me just, when we're talking about the nature of reality and the nature of truth, just picture the evolution of our understanding of the universe, right? So when Columbus got not quite here, but close to here in 1492, what kind of universe did he believe in, right? They all lived in an Earth-centered universe. The Earth was static. It didn't move. There was this kind of verticality to their existence in which the Earth was the center. Then you had all these planets around it. And afterwards, you had the sphere of the fixed stars. And outside all of that was the realm of God, right? So there was this verticality in which the universe kind of mirrored what people believed in. And they guided their existence based on this. And this influenced not just the way they live, but the way they created things. So for example, medieval cathedrals, they're all vertical, right? They're all very high. Why? Well, because as you go in there, you want to look up, right? And why? Well, because you want to commune with God up there, right? So there was like this reproduction of the macro to the human scale in the cathedrals, and it was mirrored in the belief. So things made sense, right? And this is more or less what Aristotle proposed way before the Catholic Church. But then comes Copernicus, right? In 1543, it said, sorry, folks, the Earth is just another planet. It's nothing special. Just like Jupiter, Saturn. There are 8. Well, in that time, there wasn't 8 because they only knew until Saturn. But there was then Pluto, and then Pluto is gone, poor guy, right? So there's this, which actually shows how shifty science is, right? So that's part of how things evolve, right? What we call a planet has changed because we understand planets so much better than we did before that Pluto really falls out in a sense. But so he shifted the order of things and forced people to kind of reconsider this whole arrangement that they had before, and people were very confused by this because that centrality of the Earth, which seems so intuitive, right? You walk out and you do see the sky is turning around us, right? I mean, so intuitively it makes a lot of sense. But science is, in a way, mechanism we have to break with all these intuitions, which are false intuitions, right? So we can see deeper into the nature of things. And then you cut to the 20th century, and our picture of the universe is completely different, right? This photograph, which I'm going to repeat because it's just one of the most awesome photographs ever taken in history. I'm biased, but it's true, okay? This is from the Hubble, and it's called the Hubble Deep Field picture, which that means the following, is that they pointed the telescope to a very narrow piece of sky and collect light for a very long time, okay? So they can see stuff that is really far away. So when you look at a picture like that, I say, oh yeah, Claire, there are some galaxies here. Where's the Milky Way? If you guys are real smart. Thank you. Not in this picture. Because to photograph the Milky Way, you have to get out of it, and we can hardly get to Mars. So it's a long way, folks, to get out of the Milky Way. But still, so you have galaxies here, and then you say, oh, what about these little stars? Well, these are not stars. They're galaxies too. They're just further away, right? So each point of light here is a galaxy as big as these big spirals, which are closer. And each one of these galaxies have about 200 billion, 100 billion stars, just like our Milky Way does, right? So we live in the Milky Way. Just to give you a little bit of perspective here, which is this big mass of stars, about 200 billion of them. The sun is one, and the sun has 8 planets, right? And when you look at the planets, you say, okay, that's not the whole story because planets have moons. So Jupiter, for example, has over 60 moons. So nighttime at Jupiter must be just awesome, right, to look at these moons. And that tells you that in our galaxy alone, there are trillions of different worlds. There are trillions of worlds, and they're all completely different from one another. They may be somewhat similar in some ways, but they're not. There are no two identical worlds. And then you look at this and you say, damn, you know, each one of these things is a galaxy. Each one of these galaxies has these billions of stars. And so the numbers are ridiculously staggering, right? And how do we gather information from this? Well, from light, right? And so, for example, when you look at the moon, you're seeing the moon 1.2 seconds ago, because that's how long light takes to go from the moon to us. When you're looking at the sun, it's about 8 minutes. It takes about 8 minutes for light to travel to us. As you know, the speed of light, 186,000 miles in a second, which is another ridiculous number. It basically means something like if you blink your eye, light goes 7.5 times around the Earth. So blink your eye, 7.5 times around the Earth. And it takes 8 minutes for it to come from the sun to us. And it takes 2 million years for light to come from the closest galaxy, which is Andromeda, to us. So when somebody points a telescope and sees Andromeda, he or she is seeing Andromeda as it was 2 million years ago, meaning when our ancestors were beginning to go, biped in Africa, right? That's when that light left Andromeda, right? So what that tells you is that when you look at the sky, you're looking at the past. The skies are a giant time machine looking at the past. And parenthesis here, actually you are seeing me in the past as well. You're seeing me about 1 billionth of a second ago, right? Because that's how long light takes to travel somewhat this distance, which basically means that the present does not exist. Now is a cognitive fabrication because every information we gather takes time to get to us, right? And what happens though is that light is so fast compared to how fast our brain can process this information that it seems that everything is integrated into an instant, but it really is not in an instant, So that's something like to ponder. So what does that tell you? Well, we now know that the universe is not just this, but is actually expanding. The universe is a dynamic entity. So and when people talk about expanding the universe, they always imagine that there was this big bang, there was a bomb that exploded at the beginning of everything, and the galaxies are sort of like shrapnel moving out. That is completely wrong. That is really not what the expansion of the universe is at all. The expansion of the universe is really an expansion of the fabric of space itself. It's sort of like if the floor underneath was made of rubber, okay? And I pushed a button here, and as I pushed that button, it started stretching in the 2-dimensional directions. You have 2 directions here. And you would see everybody moving away from you. You look around and say, hey, man, look, everybody's moving away from me. I am the center of the universe, right? And the person next to you says, sorry, dude, I am also seeing everybody moving away from me, so I am the center, because there is no center. This is an expansion of space itself that is stretching outwards, and the galaxies are basically being taken with, sort of like a cork floating on water, in a river, right? So that's really what's going on. And so we now know that this expansion has been going for about 14 billion years, or 13.8 billion years. Now, you put these two things together, that light takes time to get to you, and that the expansion started in a finite time ago, and that tells you that light could only travel so far within that time. And that tells you that you can only see stuff up to a certain boundary. We call it the horizon. Just sort of like when you go to the beach, there's the horizon there, and where the ocean hits the sky, right? And you know that the ocean doesn't end there, but that's as far as you can see. That's very similar. In cosmology, we have this light bubble, the fish in the bowl. And we are inside this light bubble. And there may be more universe out there. Probably there is. That people talk about multiverses right now, which is something that you may want to ask me, hint, hint, about. But you cannot see it. So it's something that is not just unknown, it's unknowable, right? Which is like, wow, so science is telling us there are things which are not just, we don't figure them out, we cannot figure them out. Unless you come up with a new physics that says that the speed of light is not the limit, and then all bets are off, right? Then you can say anything, right? When you break the conceptual structure of something, everything can go. So there is your first unknowable at the cosmic scale, right? That we really live in a bubble of information, which is the cosmic horizon, and we cannot see directly what's going on out there, okay? Okay, now just talk about material. So what is the world made of? The stuff, right, that we are made of. So we are obviously made of atoms, right? And the atoms are made of protons, electrons, and neutrons. Where would computers be without the electrons flowing around, right? And that stuff, this stuff that we are made of, and we have about 92 stable chemical elements that we have found and that exist. Everything else is unstable. And all of these things came from stars, right? So when you ask, where did the chemistry of the universe come from? Where is the calcium and the iron that makes me? Where does that stuff come from? It came from stars that exploded a very long time ago, before the solar system formed in about 4.5 billion years. And so when people say, we are stardust, that is absolutely correct. We really are literally stardust, and so we are part of this cycle of creation and destruction, where matter becomes recycled, from hydrogen into everything else, One astronomer once said something that I really like, which is like, people is what happens to hydrogen when you wait long enough, which is exactly right. It takes a long time from hydrogen to be processed into the heavier elements, and then obviously for life to develop from that primal fundamental substance. But it turns out that, this stuff, the electrons and protons, only make up 5% of the universe, right? The rest, we don't know what it is. Okay, we know it's there. It's sort of like you're going to make a cake, and it tells you, look, there are 3 ingredients. I know that water is one of them, and it's about 5%. And there are 2 others, and one is about 23, the other one is about 73, but I don't know what they are. So figure it out. How they're going to make that cake. That is how we are picturing the cosmos today. So these 2 other mystery ingredients are called dark matter and dark energy. And dark matter is most probably made of particles that have mass, but have nothing to do with us, like protons, electrons, or if you want to go deeper into particle physics, quarks or Higgs or anything like that. They are something else. And they sort of float around gravitationally. They're sort of like a cloak around the galaxies. And they are in a factor of 1 to 5. So they're 5 times more abundant than our stuff in galaxies. And people have been trying to catch these guys for about 3 decades, and we haven't been able to do that. Actually, at Berkeley, there is a very big group that has been trying to get these, and you can't, because right now, if dark matter is really made of particles, they're going through us. They interact so weakly with us that we don't even know. Just like there is natural radioactivity going from the ground, going through you right now, and even more spectacularly, the sun to fuse hydrogen into helium produces particles called neutrinos, right, which are called the ghost particles. They go almost through everything. And right now, per second, there are about 1 trillion neutrinos going through you per second, right? And we have no idea. So there's this shower of stuff that is invisible, but yet very real, right? Anyway, so we don't know what the dark matter is yet. There are many possibilities, fancy names, supersymmetric particles, but we are not quite sure. And then there is the big guy, right, the 73% dark energy, which was a complete surprise that came in 1998, which was one of these discoveries that everybody was praying to be wrong. Please go away, because it is so weird and so mysterious, really. Basically, it says that not just that the galaxies are moving away from one another, but about 5 billion years ago, they started accelerating away from one another. Sort of like if there is some kind of repulsive force pushing space apart and taking these galaxies with, okay? Now, what could do that? Well, there are candidates, right? Einstein himself put a term in his equations in 1917 where you can put a term in the equations that kind of does that, induces this kind of stretching of space. It's called a cosmological constant, right? But he abandoned it afterwards, saying that was just very ugly stuff. He called it my biggest blunder. And lo and behold, here the thing is again, sort of, or it could be something else, something like an ether. I don't know if you guys remember, in the 19th century, people believed that light traveled in some sort of mysterious medium called the ether, right? And everybody believed that, and the ether was just the weirdest thing you can possibly imagine. Transparent, weightless, and yet more dense than steel in order to be able to transfer waves that fast, the speed of light. And people believed that stuff because they could not imagine that a wave could travel in an empty space, in vacuum, right? And there comes dark energy, and it sort of looks like an ether. It's sort of the same way the air is everywhere here. There's this thing across the space that is filling up the universe, making it move outwards really fast, so fast that if nothing reverses this, in about a long time for 50 billion years or so way ahead of time, the universe is going to look completely different than it does now. So if the astronomers are 50 billion years from now, we can go talk about that later. But it's a whole other talk. But assuming that they're there and they're looking at the universe, they would see something completely different. They would see almost complete darkness because the galaxy would be just so far out that the light could not reach us anymore. So they would be sort of in an island universe, and not be able to see anything out there. So the way you picture the universe changes completely as we advance in time. Let me just make a note of what this is. So this is a self-portrait by Rembrandt, right, the Dutch painter. And if you have seen any other one of his self-portraits, they are always kind of gloomy. But this one he did when he was young, and it's called Self-Portrait in the Likeness of Democritus. Now, Democritus was the second guy that came up with the notion of atomism, right? That particles are made of little bits, right? That the matter, you can break matter into fundamental little bits. And he was also called the laughing philosopher, hence the laughing Rembrandt there. And the reason why he was called the laughing philosopher is because he believed that only if you develop your faculty of critical thinking and free yourself from slavery, the slavery of superstitious belief, can you truly be happy, right? And he, of course, reached his rational nirvana, in a sense, and he was a happy guy, and that was his nickname, right? So he was very much anti-religious belief, And in fact, Lucretius, when he wrote his famous poem about the atomistic structure of nature, he would use this image exactly in the same way that, to be able to think critically about reality is your way to break free of slavery from superstition, right? It's better not to know than to live like a fool or be fooled by belief, so to speak. Anyway, so of course, when we go and talk about what we understand of matter now at the quantum level, right? There are all sorts of technical questions that we have to ask, which are really strange. So we here live in our classical reality, right, where we can touch things and there's an objective separation between us and everything else, right? You know you have a chair outside of you, you're sitting on it. When you go to the quantum world, when you look at electrons and you study them, everything goes down the drain. First because you don't see an electron, right? You don't see a fundamental particle. What you do see is a click in a detector, right? Or a little curve in a detector. And that thing appeared there after being amplified a lot by these photomultipliers. So the electron, whatever that is, creates some sort of transfer of energy and momentum, and this thing is amplified, and then it becomes a click that we see. There's a huge gap between the reality of that electron and our reality of counting or looking at data in a computer screen, right? And so there is no immediate connection with the very small, so to speak. And so when you look at the equations that describes these things, right, and they were all developed to kind of make sense of data, right? I mean, people were making experiments with electrons and fundamental particles. They were very strange, caused a lot of distress, including Einstein, right? Because what was apparent is that you could not have a deterministic way of thinking about reality anymore. Everything was really probabilistic. So the equations would say, look, an electron could be here or could be there with a certain probability after you measure it. Before, if you take it literally, the physics of quantum mechanics, you can even say an electron exists until it interacts with a detector, right? So that brings this interesting philosophical question, which is, hey, if the electron only exists when I interact with it, I am creating reality by the way I interact with reality, right? So is reality dependent on us, like an intelligent observer, or is just the detector that is creating the reality? There are all sorts of weird, complicated philosophical questions that I go into a lot of detail in the book. I can't in 40 minutes, obviously. But the interesting point here is that in quantum physics, you have this deep connection between the way we study reality and the way the reality manifests itself, as opposed to this separation that you see a rainbow, there is the rainbow, right? And with the electron, you can see an electron as a wave or as a particle, depending how you set up the experiment to study an electron. So what is it? Is it a wave? Is it a particle? And this is sort of like an endless debate, which has to do with this interpretation of quantum mechanics. On the other hand, it is the most successful theory we have in physics, right? It is, when you make measurements with quantum mechanics, you get a precision to 12 decimal points. There's no theory that can do that. I mean, gravity sucks compared to that in terms of precision, and it's much older, right, than quantum mechanics. But when you interpret quantum mechanics, the whole notion of how deep can you go into reality becomes very convoluted, and essentially also the fact that there is a fundamental randomness to the way these particles behave that we cannot predict. So you cannot come up with a theory that describes if an electron that you're going to measure is going to spin this way or that way when you detect it. So to make it simple, right, let's say the electron can do two things, go counterclockwise and clockwise, right? So you have a 50% probability of when you detect it being this way or the other way. And when you detect it, you're going to find out. But you cannot build a theory to predict that. So there's a fundamental unknowability at the very core of matter. So you go from the edge of the universe that we cannot know to the very core of matter that we also cannot know with this precision that we want, right? So these are two sort of very distinct unknowables, and they don't seem to be going away. In particular, the case of quantum physics, I was really upset that they didn't get the Nobel Prize this year. They gave the Nobel Prize to guys who developed the LED, which is fair enough, right? Very important, LEDs, right? But I was rooting for the guys who made these experiments with the fundamental questions of quantum physics. In particular, can you find a theory that could describe the electron through local forces, that could explain if it's going to spin this way or that way? And what they found out, which is really an amazing thing, is that it's impossible to build what we call a local theory of quantum mechanics that explains this probability as the result of some fundamental underlying causality, right? So Einstein was wrong. There is no way you can create a theory that explains this basic random behavior at the fundamental quantum level, which is great for cryptography, right? I mean, this is going to be the essence of quantum computers. So there's this whole big quantum information theory framework that is emerging precisely from this. But on the other hand, from this perspective of how much can we know of the world, you have a fundamental block right there. All right. And finally, I just wanted to make a point that this is a quote from Democritus, right? So he knew all these things, but he knew also that, careful when you talk about truth, And a lot of scientists, many colleagues of mine, make these big, bold statements that should not be made in public, because sometimes they push what science really is doing or can do way beyond what we really are doing. And that is a disservice, I think, to science, especially nowadays when there is so much criticism to what science can do. You have all the global climate deniers, right? We say, oh, these scientists, they keep changing their minds. Hey, look, they found gravitational waves from the Big Bang, right? In March, there was this big stuff actually here in Stanford. I don't know if you guys know the science people, about Andre Linde and all these guys, there will be Nobel Prizes all over the place, and it's BS, right? So they had a press conference before they had a peer review, and that is not what you should be doing with science. So that just gives ammunition to all these guys that want to say that we don't know what we're doing, right? So the book, the way I'm bringing this together, is really an effort to bring back this integrity into science. Say, look, this is how we think. This is how scientific knowledge is constructed. Let's be very careful about these big, bold statements about, we understand the Big Bang. We do not understand the Big Bang at all. There are all sorts of fundamental questions we have no clue about. And you have to be very careful, especially when it's like Stephen Hawking that says something like this. Anyway, just to the last couple of minutes, I wanted to talk about the last part, the cognitive part, right? And first of all, we have to say sorry to Descartes because there is no dualism, right? There is no matter and soul, right? There is just matter, right? And the big question in cognitive neuroscience is exactly how does the brain engender you with your sense of self, right? So you have 85 billion neurons. They're all connected to, which is about the same as stars in a galaxy, which is kind of a cute image. And they're connected to one another by thousands of synapses, right? And the question is, how is that giving you your ability to think and to be yourself every day, right? You wake up the next morning and it's still you, right? There is some sort of continuity here. And we are all made of the same stuff, and yet we are so different, right? So how exactly is that going on? So below, at the bottom of this debate is really the question, can we build artificial intelligence machines, right? I mean, is that something that we can do? And the effort for, the movement for starting this started at Dartmouth, actually, in 1956. There was a conference there which started the artificial intelligence community, so to speak, right? With Marvin Minsky and Claude Shannon, some very smart people. And they said, of course, we can build a machine that can think, like a human. You have to make a distinction here. One thing is to think. The other thing is to think like a human, meaning emulate a human brain through machines. And they were convinced that was happening real quick. It's just a matter of a few years. And here we are, right? I mean, you know this better than I do. We have the fastest computers now at about 10 to 16 floating point operations per second. The brain, it is estimated, because we really don't know exactly, but at about 10 to 18. So we're almost there. And this guy called Henry Markram, who got the biggest grant in the history of science, the Human Brain Project in Europe, 1 billion euros to emulate the human brain in every possible detail, says, or is convinced that by 2018, we will have machines that will get to the 10 to 18 floating point operations. And so if that's true, is that all you need? that's the real fundamental question, right? And can you just then input all these 85 billion neurons, connect them, and they even want to do the flow of neurotransmitters through synapses. You know, they really want to create some sort of hydrodynamic code that can mesh with the sort of binary flip on and off, you know, from the neurons. It's a beautiful, ambitious project, but the question is, can you do that? And so, well, the problem behind this, and there is a group of philosophers that have the best name ever, it's called the New Mysterians, right? And the New Mysterians say, we can't do that. We cannot understand the human mind, and certainly not reconstruct it in a machine. You may be able to reconstruct or create some mind, but not the human mind. You know, and that's an important distinction because we cannot understand consciousness, right? So this is what's called the hard problem of consciousness, is the notion that one thing is to look at a painting and monitor all the neurons that are flashing because you see the painting and you react to the painting emotionally. The other thing is to understand the subjective experience of what it means to look at the painting. There are two different things. There is a disconnect between the two things. And also another way of saying is that when I look at a painting and you look at a painting, we're going to see the same information, like there is the painting, right? But I'm going to react in a very different way from you because I have this consciousness and this experience, subjective experience, which is not the same as yours, which another way of thinking, a third way of thinking is that the brain cannot figure itself out. Right? And no computer simulation can simulate itself or include itself in the simulation, right? And that's a problem in computer science, right? I mean, you cannot have a computer simulation that includes the computer in the simulation itself. So we have a hard one, essentially, here, right? And that is the third dimension. And of course, I couldn't come here and not mention that, you know, this issue of the question of living in a simulation or not is actually a very serious, complicated question. And we cannot know right now if we are living in a simulation or not, right? There was a paper last year from some colleagues that they said that if we are a simulation and they use a lattice to simulate reality, which is, say, a square lattice, right? For example, a cubic lattice to be three-dimensional, every lattice, when you simulate something, has a spatial resolution. And in order to probe very short distances, you know, you can shoot particles at very high energies to probe these distances. So it is in principle possible to tell what would be the spatial resolution of the lattice that is simulating us, right? Because the aliens or whoever they are would need to save memory, you know, by doing this lattice. No lattice is infinitely thin, right? You have to cut off at some spatial resolution. And so, you know, the point being here, well, but, you know, if it's very fine, it's way beyond anything that we could create right now in terms of energy, say at the LHC, so we could be fooled, and it's really a hard question to answer. Sort of like The Sims, right? Think of The Sims 50 years from now, and we know that we are playing The Sims and they have absolutely no autonomy, right? But 50 years from now, you can imagine that Sim characters are going to be so developed and so self-sufficient, they're going to believe that they are autonomous individuals. So they will believe that they are real. And, you know, our grandkids, whatever, will be playing with them, and they aren't, right? But they don't know. So the question is, can we know, right? And that is the other complicated question. So just to wrap up, what is this notion of the island of knowledge then? Well, it's the way we really construct scientific knowledge, right? So you have an island, which is where you put all your knowledge, and this island can change in time. It can grow as we understand things. Sometimes it shrinks like the ether, right? And it be all jagged because things are not linear. But there is an island that is on average growing, and it's surrounded by this ocean of the unknown, the stuff that we don't know about the world. And the idea then is there are two ways, right? So the naive people would say, hey, the island of knowledge grows, 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 and eventually there's not going to be any more unknown. It's the end of science. A lot of people talked about this, and that is complete nonsense, right? Because, as I try to explain here, as the island of knowledge grows, so does the shore of our ignorance, which is the boundary between the known and the unknown, which basically means this: as we know more, we become equipped to ask questions that we couldn't have contemplated before. going back to the example of the microscope, right? Nobody could have predicted that life would have been that small before the instrument opened a completely different reality to people and allowed people to ask more questions. So the notion of final truth, which implies complete knowledge, is absurd because you can never ask all questions. So if you can't ask all questions, how the heck do you know all the answers, which is a much harder thing to do, right? So that's the essential idea. And so you have this map over there, right? And you have these unknowables that I mentioned briefly here, right? So to take this into context, it's not like, oh, damn, this is such a defeatist kind of idea, because it isn't really. It's really about how we make meaning in the world, right? We are always trying to go beyond our limits, and that's exactly what it should be. And it's really searching that makes us matter. It's wanting to know that gives us value. You know, it's trying to find the meaning that gives us value, not necessarily arriving at the end of everything. And so to conclude, you know, from the way I picture things here, what we call reality is really a shifting map of ideas, because as you've seen, you know, the fundamental core of reality has changed as our knowledge of nature has changed in time, and there is no reason to believe that that's not going to continue, right? So we can talk about what we know now and what we knew before, but not saying that this is the end of the story. This is just one beginning, and there'll be many, many others. And that's it. Thank you very much.
Thank you for your talk today. I don't know not about theoretical physics. So what are the major problem there? And if we solve them, what are the major implications? What can we do that? What can we do that we cannot do now?
Well, nobody can answer that question, right? Because, I can tell you what the big problems of physics are. I mean, it's kind of a boring, but there's dark matter that I mentioned. You know, what is the nature of dark matter? What is the nature of dark energy? Turbulence. We don't know turbulence, or what causes turbulence in fluids. We don't know what's beyond the Higgs particle. You know, are there any other particles beyond that? So there are many fundamental questions. Is there a multiverse? You know, is our universe the only universe that exists? Or are there multiple universes out there with different laws of nature, and ours happens to be the one that allows for stars and people to exist, right? And how can we tell? See, the multiverse has a very fundamental problem too, because if it exists, we can't know, because the other universes that are part of this multiverse are beyond our light bubble, which means we can't get information from them. And so physics, especially this sort of out there, more abstract physics, is going through an interesting time now where some questions may not be answerable, you know, and yet the ideas are very nice and compelling. They're interesting, right? But we may never know if they are true or not, right? So that, to me, is a serious problem, you know, that we have to deal with.
You're really curious if you had, say, infinite resources and infinite time. You presented a tremendous number of questions. Which question would you try to answer?
Right. Well, from a realistic perspective, like what can we figure out first? I think dark matter. I think in the next 20 years we'll figure it out. You know, either it's there and we'll find it, or it's not there and it's something to do with our theory of gravity. Because believe it or not, even though it started with Newton, you know, in 1686, it's the least understood of all forces of nature. We understand electromagnetic forces and the weak and strong nuclear forces much better than we understand gravity. So people are beginning to say, is gravity even a force? What the heck is going on? You know, because it's only attractive. And so I think dark matter would be the one, but the question that I'm most fascinated right now with is, which has not to do with this talk because that's my research. I'm using information theory to describe the emergence of complexity in nature. So how can you quantify, using information theory, the complexity of objects, you know, from a star to a leaf, you know, and the way you do that is by every object can in principle be described by mathematical functions. These mathematical functions can be decomposed into waves, and you can find out the weight that each one of these waves would have for that particular object, and you can extract some information from that. There's a whole theory from Claude Shannon, the guy that was the AI guy. And I'm very interested in that because I think nature has sort of we always know that nature always saves energy, right? I mean, everything that happens in nature uses the least possible amount of energy. And I think it does the same with information, that all the shapes are optimized shapes, that there's no, I'm trying to construct that principle. But it's very different from these questions here. Yeah, thanks.
I find it hard to disagree with all this, but I don't talk to scientists very much. And so I'm wondering, why did you choose to write this book with this topic right now?
Right.
Do you think this message needs to be delivered now?
Yeah.
Is it a welcome message or is it unwelcome for anyone?
That's a very good question. Thanks for asking. I think it's a very important time to write this book. I tried to hint at this in some statements I made about, big, boasty pronouncements by scientists saying that science is doing this, science has solved this problem, and that is just not true. So I think that what we need is sort of like bring back this kind of integrity, really, to how science is done and what science can do, and so that we protect ourselves from these attacks, because science is under attack, right? I mean, 28% of Republicans only believe in that the weather is getting hotter because of we call it the Anthropocene, and that's really bad. And so we need to do something about that. And it doesn't help to have these pronouncements. That's one. Second, I think there is a big confusion about how science actually works. How do we gather knowledge about reality? And I think to clarify these concepts is really important to people. So how instruments play a fundamental role in all of that, the limits that they impose on our knowledge. It's great because otherwise you make science into some kind of religion, that will solve everything, and it's just really not like that. Science is a product of our creativity, and it's as wonderful and fallible as we are. And I'm trying to bring this sort of sense of grounding. But yeah, and you ask how scientists react to it. The humanists, believe it or not, are taking this much better than the scientists. Some scientists say, now you're basically saying that we can't solve everything. It's like, yeah, so what? Be real, right? I mean, we can't, period. That doesn't mean it's bad. It's fine, But so be it. Thanks.
Hey, I had a question. Like, if you know the wave function of all the particles in the universe, can we determine what's going to happen tomorrow, for example?
We can't know the wave function of all the particles in the universe from a fundamental principle, which is, in order to know that, you would need to know the position and velocity of all the particles at the same time, instantaneously, and you just can't make that kind of measurement. So it's the initial condition to solve this wave equation that we can't get, right? So no, we can't. But you can say that there is something called the wave function of the universe, but that's a much vaguer way of thinking. There was a guy called Laplace that said that if there was a supermind, this was in 1810, if there was a supermind that knew the position and velocity of all particles at a given moment in time, you just crank the laws of physics, mechanics, and you can predict the future. Like that I'll be here talking right now, right? You would have asked that question. But that is fundamentally impossible for that reason, and also because of the indeterminacy in quantum physics. You can't know the position and velocity with arbitrary precision of a particle. But that would be nice. But we can't do it.
But can we assume that such position and velocity, the wave functions exist, so even though we can't find out, do we assume that such a wave function exists and so our future is already determined or something?
I don't think so. Because, remember, I don't know if you're here when I was talking about the randomness at the very fundamental level of particles, and you can't get around that. So there is no way of, and the only way we could do that is to create what we call a local theory that explains cause and effect at a point in space and time. But what people have found is that the theories can only be non-local, which is really weird. It has something to do with entanglement that I didn't have time to talk about. But And so you're really stuck. You can believe that there is something which is an ultimate reality out there. Probably, right? I mean, the universe is out there, right? But that doesn't mean we can get to it completely. We can only get to it partially, which is okay. The more you see, the better it is.
You mentioned about consciousness at the end, and you also mentioned a couple slides before that that everything is matter. So I was wondering if you are aware of models that explain consciousness as a non-matter entity, but still explain everything else with that kind of a model. I was just curious if you had exposure to that kind of models and what your thoughts on that are.
You mean models, scientific models?
Yeah, they are non-mechanistic models. As you rightly mentioned, there's only so much. Each tool has a range, you mentioned. So when you exhaust the tools that can deal with matter, doesn't mean that there's another reality besides that.
Okay.
So how do you understand that?
So the way the sort of typical response to that is something called the binding problem. And the binding problem is the following. If the brain is matter, right, and there is something else out there, but call it whatever you want, right? And is this something else interacts with the matter of the brain, that means it's exchanging some kind of energy and momentum or something which is really physical. And so you should be able to measure that. And the binding problem is that you don't know how to bind this immaterial with the material without producing some effect, which is a physical effect, like, this. And so this is a fundamental problem. So you can believe things like that, as an assumption, but it would be very hard to verify this scientifically. So from a scientific perspective, you go, I don't know, right? I mean, I hope not. I hope it's really all matter, and matter is awesome already. Look at what it does, right? I mean, and the fact that it's such a complex problem, the emergence of consciousness, doesn't mean, and that may be unsolvable, doesn't mean that it needs to be explained by other means that cannot be verified scientifically, unless you kind of integrating in your mind, other ways of knowing, which is fine. I mean, people do that. I'm not Richard Dawkins here. I'm not that kind of guy. And I'm totally okay with that. But from a scientific perspective, it's very hard to justify that.
Thank you, Marcelo.
You're welcome.
At Google, we are primarily concerned with universal access of knowledge. So I think when you talk about distrust of science in general public, at some sense, right? Do you think misinformation is also a contributing factor? And what does scientific community, use? Like I believe there will be some pages somewhere on the internet which say Pluto is classified as a planet, right? So how do we get people the most up-to-date scientific information, and does everybody have to go through reams of scientific papers and journals to
You can read my blog on NPR. No, I mean the point is there is no Google Science page yet, right? Why not? So you should get a team of consultants from different areas of science that will give you like a weekly bulletin with critical commentary that people can go to. Hey, it's not a bad idea. But the point is there are some sources that are trustworthy, but I was also mortified when I saw the Scientific American, the cover of Scientific American this month, talking about precisely this measurement of gravitational waves from the Big Bang, right? And it makes a big bombastic statement, and and inside, when you turn the pages, that if it's true, very tiny, right? Which is a marketing thing. They got to sell magazines, right? So that's where the confusion starts, okay? And that's where the media, hey, we want to attract viewers. So the God particle with the Higgs has nothing to do with God. Do you guys know the story behind the God particle? So this guy called Leon Lederman, who is Nobel Prize winner, who has been looking for this particle for 20 years, okay? And he was writing a book called The Goddamn Particle because he couldn't find it, And his editor said, take the damn out and you're going to sell many more books. And he did. And that is the real story of the God particle, where it came from, because I worked with him, at Fermilab. So anyways, But people love this, right? So, science and religion are being, scientists are finding God through the particle accelerator, right? That's awesome. So that's where things get murky. And these blogs, especially when I write about climate change, at NPR, it's a war zone. It's unbelievable how people get offended by the fact that we're messing up, and instead of doing something about it. It's really remarkable. So there's no simple answer to your question. One thing that possibly could do is that scientists should go to schools and talk to kids more than they do. They're very, how many kids know scientists really in grade school or even middle school, right? And I think that's something that we can do, that makes a difference. Or the Google Science page. Hey, thank you.
Thank you.
Thank you.